that was quite an adventure with the whole 3:1 and 3:2, wasn't it? So we're going to finish up chapter 3 with the last strip. There's only 2. Who would have known that the first one was almost 2 hours worth of information? So we're going to glue in my strip for 3:3. So there they go. Okay. And unknown demand right there. So at the very end of the last video where you were taking notes on 3:1 and 3:2, Becca Delosier had a pH little piece that I put on there just to give you a heads up on just some other things that happen when you have aqueous systems. So let's read what this says. Small changes in pH can cause significant differences in enzyme function and rate. And it's not just enzyme function and rate, but in general that's going to be why that biological systems are so tightly regulated, because the enzyme works because of its shape. So that structure is the reason why it functions the way it does. And pH can pull and change at the shape of that enzyme. So if you think of it, a lot of times the reason why whatever we have, like a pen, works the way it works is because of the shape that it is. And so if you start messing with the shape, it's not going to function the same. So we want to explain why small pH changes, like changing just what seems like a little bit to us, 7.6 to 7.2, can have really huge effects, and why the body so tightly regulates it. And here's the reason. pH is logarithmic, which means everything's in a power of 10. So let's just put that down there. So pH changes. So this isn't just like 0.4 and it's a little tiny something. It's going to be in powers of 10. So what that means is if you go from a pH of 6 to 7, it's a 10-fold change, not a 1. So that's what you have to keep in your head. So really this is a large change. So let's talk about what pH is. pH is the hydrogen ion concentration in a solution. So this is concentration. So it's a measure of the hydrogen ion concentration. And we can do math around these problems. So when we look at this, let's just get a feel for what happens with pH. So if we look at pH 7, if we increase that pH to pH 8, as you go up, you have less hydrogen ions. So we increased here, so this is going to be a 10-fold or 10 times decrease in the hydrogen ion concentration in that solution. So that would be the same. Let's just turn around and go this way. So now if we're at a neutral pH, that just means that you have the same concentration of hydrogen ions as hydroxyls, and you decrease the pH, a decrease of pH is an increase in hydrogen ions. So they're opposite from one another. So here we would have a 10-fold increase in hydrogen ion concentration. So let's do some math here, and I don't even know if I've got a graphing calculator with any batteries, but we'll work on that. So this is what pH really means. This number is the exponent that goes with the power of 10 as far as to get a real number for hydrogen ion concentration. So this is what I mean. A pH of 7 would be 7 as the exponent, so it's 10 to the negative whatever the pH is. So that's how you're going to write your hydrogen ion concentration. So in that case, you'd have 10 to the negative 7. is going to be your hydrogen ion concentration. And you can put this in your calculator and it'll give you a number that's going to be converted to just scientific. So a lot of times on the calculator it's EE. So we can do some things that are a change. So I think I've even got a strip where we do some problems. I think what I'll do is I'll put that strip over here and we'll do the problems together. And I'll show you how to do the math and the calculator all together on those. Because that question's really not about the math of it. It says explain why small pH changes, like just going from 7.6 to 7.2 can have such large effects. And the answer really is because pH changes are in powers of 10. And so they're exponential different change. Okay, so because of that, and because systems are so tightly regulated, what do you do when you're in an environment that's not going to be conducive to keeping your pH the same? So you use buffers. So this is 1 and 2. So buffers have the ability, so a buffer is just a chemical, and they have the ability to accept extra hydrogen ions. So as that pH is going lower than you would want because there's more hydrogen ions, the buffer can accept them, or it can release hydrogen ions in order to maintain. So it's almost just like a sponge for hydrogen ions. So buffers have the ability to release hydrogen ions and they have a range that they work in, accept hydrogen ions. So what they can do is that they soak up that extra or they give back a little bit more, and this is going to be a way to maintain the pH of a system. Now again, because we're living things and chemistry's in isolation in a beaker, you can add a buffer solution and you can maintain a pH even though you're adding things that should change the pH. The buffer will work up to a point. But in living things, there's lots of different buffers. And they work really tightly in regulatory loops. And so their job is regulation. Because that's the key. All right, what's the next one? Because that's the role. The role is to maintain the pH. And they do that by either contributing or accepting hydrogen ions. So in this particular, this should be a plus, situation, it's from a figure. And so the main thing we need to focus on, we don't really have to focus on the figure, is lots of things go through calcification. And so you've got calcium, and you're going to predict what would happen. So you're going to have calcium, you've got carbonate, and you end up with calcium carbonate. So this is what the shells are made out of marine organisms. And the main point of this is a lot about just understanding how reactions go. So I'm going to probably just rewrite it right here. So it says, predict how using higher concentrations of calcium would affect the experiment. So you've got calcium, and I'm not going to write all of the rest of it. I'm just going to write out the basic. And you've got calcium carbonate. And they're saying that calcium is going to increase without having additional carbonate. You won't make more product, but you have a push toward making more product because you're increasing one of the reactants. So that's what they're trying to get at. So let's just put on here that is the calcium That drives me nuts. Goodness, so sorry. You can see my eyes are watering. I don't know what I did. Okay, so their whole point is we're going to increase the concentration of one of the reactants. What's going to happen? Well, here's what tends to happen in the questions that we use. As long as the other reactant is what's called in excess, it just means more than you could ever use. You can increase the concentration of calcium as long as carbonate is in excess, and you will drive the reaction toward more product. And that's what happens a lot of times in biological systems, is that one of the reactants is plentiful and the other one's tightly regulated. And because it's tightly regulated, then you can regulate the product. So if you increase the concentration of calcium, you'll move more toward the product. I know that's not what it sounds like they're asking, but that is what they're asking. So if you can just keep it in your head that if this means it's plentiful, and I'm going to use my little 3 dots, so therefore it's not regulated. It may just be something that can't be regulated because there's just so much of it. Then usually what happens in a biological system is you lock down the other reactant. And so you can do what's called sequestering, you can do a lot of things, but you're going to highly regulate this, where'd my G go? The other reactant. And then at that point, you know, it's just like having a whole bunch of this ready to go. And then when this shows up in a higher concentration, then you can drive more product. But you know, it's supposed to go in both ways. But you're going to push it toward the product. Okay. It's crazy that that's all there is for this strip. But I'll go find that pH problem set. And I'll do it separate. Because you do need to know how to use your graphing calculator to calculate those. All right. Thank you for being with me. You're the best.